Now we've talked about the simplest case where the data are essentially level, or maybe level for a while and floating to a new level, but level at least for a while and then maybe level at a new altitude later. It's time to think about trending data, and there's a variant, a two-equation model, because you have level and trend in this kind of data, and it's called Holt's method. Mr. Holt is the one who proposed this, and I'll show you the two equations and then we'll talk about what they mean. It involves a kind of obvious extension. So we have a smooth at time t again, and it looks almost like the previous equation. We have alpha times the current actual data value, and then we have 1 minus alpha times something else. And that something else used to be the previous smooth. But if we have trend, the previous smooth is obsolete. It's not in the middle anymore because the data are trending up or trending down. So instead of using the trend, a simple trend, we say the current level that we think the data is at is the old level plus the trend that we were seeing at that time. So this has elevated us, the trend has moved us up or down, and this is where we think the middle was last time, and then this is our idea of where we are now. So where we are now, as we've calculated it, plus what we're seeing, gives us a new estimate of the middle of the data. And then this B, which is the level, which is a trend. Imagine the data is doing something like this. We're thinking of B. Here's, you go over 1 and you go up by B. The B is the trend. That could be changing at each time too. The trend doesn't have to be a straight line. It could be flattening out a little, accelerating a little. That can change, and we want to track those changes as well. So we have a corresponding equation for that. We have a second parameter, we'll call it beta. It's just another knob. We have two knobs now. And we have beta times something and 1 minus beta times something else. And we're saying we'll do an exponential smooth on the trend values as well. So this is level, and this is trend. One equation for each feature. And what's in here is just our previous estimate of what the trend was. And here we have a new estimate of what the trend would be. And the simple, less good way to do that, to fill in this blank, would be to say, well, here's where we are now, and here's where we were last time. So that's the change in the observed data. So this must be an accurate current estimate plus noise of the trend. But we don't do that. We do something one step smarter than that. We say both of these numbers are truth covered with noise. So let's say if we've smoothed out the noise here, the trend is our current estimate of where the level was is compared to our previous. So this one feeds into this. And these two equations are Holt's method. And we have to choose an alpha and a beta. And if the trend is changing a lot, but the level isn't changing too much, then beta will be big and alpha will be small. But this is an elaboration to allow for two problems. Where's the middle of things and what's the trend? And then finally, for a forecast, if we want to forecast at any time now plus h, we would start at the current level, and then we'd make a trend adjustment, and we say, we think the trend is B of t, and we go h ahead. So we would see a data set that might be looking something like this. Here, the trend might even reverse. We'd smooth through to find where we think we are in terms of level and trend, and we would make a forecast like that. That's how we would extend from the simple case of a drifting level to a level that could be drifting and then definite trend, sustained drift in the level. And that's Holt's method. And the next one obviously is the full Monty. You have level, you have trend, and you have seasonality.